Yeah, so I was really, like my love for math and statistics since I was young. So that really brought me to this field, but particularly like the application of that and like the power that it has to really like make an impact in people's lives. When I was, PhD student and, working at the hospitals, like every single day, like you see, like asthmatic patients and like how they're just like struggling to survive day by day. And you have the tools in your hand, like, then, I thought that, like, why not? So I was dealing with a lot of data, and it's really hard to not use statistics when you have a lot of data. There's even like a department called biostatistics in my field that are used for clinical trials and everything. But it's not the only tools that we use. Also physical modeling, together, like our understanding together with statistics can really enhance our can really deepen our understandings for the field. And in a sense, the results of my finding has really dig down to mechanistic understanding to that level where you can actually interpolate from those huge data sets, what's mechanistically wrong with like asthmatic lungs versus a healthy lung. So in that way, it really changed like the way that treatments are being done right now on patients. So I really think that's like making a big impact, but combining statistics with other understandings of other fields to really apply to a particular application that's making an impact in people's lives.
Okay.
I guess maybe like the questions would be like how one like cannot, like it's almost it's almost like unavoidable that we use statistics in our work. Again, because of like the size of the data that we deal with, and to make any inference from the data that makes sense. Because right now, when we're dealing with like its human, body, it's really a complex system. So there's so many random events that happen there, but how do you actually filter out the things that actually are meaningful from there? It's almost unavoidable that we have to use statistics to really find something of meaning among those huge data sets. Yeah, in as much as I wanted to say everyone could benefit from this work, but I really think realistically, people who have passion in this field and continuing to work. So I feel like what I built through those 5 years at MIT, with my on this project, could really be built on, and I have plans to actually open source the model. So maybe I just briefly talk about the model that I've made. It's mostly using non-invasive medical imaging devices, PET and CT, and then from there interpret physical meanings and quantifying mechanisms that are missing or that are absent from asthmatic lungs. Yes, so I wanted everyone to be able to access this, and even though currently, like with this particular medical imaging device, it's not accessible by everyone to have that data, but one day when we do, then math and statistics will become like a really, really powerful tool for everyone to really track their health, to make predictions in advance, and live like better and longer lives.
Beautiful.
It's not online yet, but I talked with my advisor, and he's totally fine with it. He's like, it's your decision because it's your work. I think that's a lot to do in this field, particularly, applying math and statistics into understanding the data. because a lot of the times people are looking at average, and that's really, there's so much variability and we're only capturing part of it. So how to have an integrated system where you can, find synergy among different data sets, from different patients, but at the same time, like not lose the granularity of, inter-subject variability. So, I mean, for the field that I've been involved with for 5 years during my PhD, a lot of models are very traditional. They are a lot of them did not incorporate statistics into them. So with that, a little more understanding can really enhance and take this to the next level. There weren't just one most difficult challenges. I think sometimes you feel like there's a series of challenges that you go through, and a lot of times it's a struggle to not give up on yourself. I still remember, I think in the middle of my PhD, I was feeling like, is this like really for me? And then I go back to like a place of my inspiration. I work at the hospital, so seeing patients and feeling like, well, if I don't do it, like who will? And that really brought me back to a place where I can find like strength to work again, to really dig deeper into the data, and like, even though sometimes it's a very mundane work where you just by yourself and trying to like rack your brain to like use your knowledge and understanding. But on the other end, there are people who might not know where this knowledge comes from, but in the long run, you know that you've contributed to the field, and that's all that matters. Yeah. So again, I guess how I surmounted them is really going back to where I feel like most connected to. And I guess for some people that, you can have like different reasons, and yeah, not giving up on yourself, because like you're the only one with this mission in your life. So, find our strength and find our voices, and really, no matter what people say, like if we stick to it till the end, like we'll see, at least we'll be proud that we didn't give up on ourselves. So that's kind of my creed. And yeah, I guess on the same ground that one falls, one rises up. So if it's really difficult for you, that means that if you're really struggling a lot, that means that you have a mission in that process. So I try to take it that way, and I don't claim I have the most difficult time, because there are probably a lot of people out there doing very difficult things and trying to change the world. I really admire people who can like really live up to their passion like consistently every single day. Yeah.
Perfect.
Yeah, so even now that I'm not working in that lab anymore, but my work is being continued on by PhD students. So I guess before, the continuation of work is really important, even though you found something like really great and you didn't contribute to the field, but if you're not there anymore, someone has to go on. So then I thought of the idea of really open sourcing my model and making it really easy for people to use. And later on, when the accessibility to data, medical data catches up, then I think this will be really a turning point. I use MATLAB and I code in SAS.
Okay.
Yeah,
And then
SAS is another. And mostly actually it's probably too simple, but I just use MANOVA to look at,
yeah, that's great.
We, traditional and conventional treatment for asthma is using, a bronchodilator, a puffer. So you inhale bronchodilator so that the drug particle goes to the part of the lung which is supposed to constrict, to really help that region dilate. Well, what turns out is that in some cases, in severe asthmatic patients, that exacerbate the disease, and a lot of people didn't really understand why. So my work was to dig deeper, not just to provide an answer to that, but really go back to the fundamental question, is that how do you treat asthma? So, and then I found that I can quantify different mechanisms that can cause asthma that are currently being projected as the really important mechanisms. So quantifying that with data and making causation statements, those are kind of like what the value added from my work. And yeah, in a sense, there was one field we were looking at the effect of smooth muscles. Smooth muscles are muscles that are in between the walls of the airways, the air duct in your lung. And a lot of people think that because overstimulation of that actually caused extreme closure of the airways. And what we found is that the effect of that on the total lung function is very small and not statistically significant compared to other effects, which is the inverse effect, the dilating effects of the parenchyma, which are the tissue surrounding the airways, being able to stretch open the airways. Those are preventive mechanisms that are not existing in asthmatic lungs. So we found the mechanism and invalidate one mechanism that has been extensively growing. A lot of money goes into that research field. And so I hope that this at least helps steer the directions and attention from people who just keep going deeper into the field that might not actually make a big difference. When you look at the entire complex system where all the parts, the airways are connecting to one another, the millions and millions of airways within the lung. So people have studied one airway and making an inference to the entire system. And my model actually put that little pieces together and try to understanding from there, like a slight perturbation in one, how can you actually how can you actually understand the global behavior from a local phenomena?
Fascinating.